Hello, I'm Wojciech Czerwiński, and I will tell you about new techniques for universality and unambiguous register automata. And this is a joint work with Antoine Motet and Karin Koas. Okay, so what's my plan? First, I will introduce the basic notions, in particular with which are in the title. And then I will give you some motivation of our work and the context, what was known before. And then I will tell you what were our results, summary of results. And then I will illustrate our techniques as the title talks about techniques. This is maybe the most important point of this talk. This illustration will be on some simplified, let's say, case. Okay, so first of all, what are register automata? These are automata, these are finite automata, but additionally to standard finite automaton, they have a number of registers. And they read finite words, but over some infinite domain. And as usually, this infinite domain can be only compared for equality and non-equality. We can assume that it's any countable infinite domain. And usually we assume this is just natural numbers. So typically our letters are 1, 2, 3, etc. And how the registers can be used, they can keep these data values. So letters are called data values. These data values from n. And how a transition. So such a register automaton, it has some initial, we call it location. What is often called state, we call location. So register automaton has an initial location and has a bunch of accepting locations. And in initial location, you can say it starts with empty registers and how a transition can look like. So first of all, it can, of course, change current location to some other location. And transition is fired if some condition is satisfied. How such a condition can look like? It's a Boolean combination, finite Boolean combination of equalities and non-equalities of register data in the register, and the current input data. So, for example, a transition can say, I can be fired if current data value is equal to the data value in the register number 3. Okay. And what is the effect of transition? So it assigns new values to registers. So for example, like current data value can be put into register number 1 and number 7. And register number 3 can now keep the previous data value from register number 4. What is important here that in our model so there are many different models of register automata with a bit different properties, and here we disallow for guessing. So we cannot put to our register a non-deterministically guessed data value, which haven't occurred before. We can only put data value which we already had in some of the register or the input data value from the word. So maybe it will be useful to to look at some example of language which can be accepted by such a register automaton. So typical standard example is these words over, let's say, natural numbers, such that first letter, first data is equal to the last data and only to the last data. So how we can make a register automaton which accepts such a language? At the beginning, automaton stores the first letter into the register. We can do it with only one register. Then it proceeds through the word, checking that input data are different from the datum in the register. And at the end of the word, it checks that indeed this last data value equals to the data stored in the register, so also to first data value. Okay, maybe I can tell you a few words about guessing here. So if we would have guessing, we can accept some other languages. For example, we can accept a language of all words which such that last data value that did not occur before. How to do it? At the beginning, automaton guesses the last data value, stores it in the register, goes through the word while checking that other data values are different than the guess data value, and at the end of the word checks that guess data value equals indeed to the last data value. And this, as far as I know, cannot be done without guessing. Okay, so this is our model of register automaton. What is unambiguity? This is some restriction of non-determinism. We can say that register automaton or finite automaton or automaton with counters or stack is unambiguous. And we say that general sum system is unambiguous if for each word there is at most one accepting run. So either a word is not accepted, so there are 0 accepting runs, or it's accepted, but then there is exactly one accepting run. And it's known that for non-deterministic systems which are unambiguous, many problems can be done more efficiently. For example, universality problem for what I call UFA, unambiguous finite automata, is known to be in p-time. Non-deterministic for non-deterministic systems, it's automata, it's in general p-space complete. Yes? And also equivalence for unambiguous finite automata can be done in p-time. For example, for vectorization systems with states, language universality problem, yes, it can be done in exponential space, while for this is in unambiguous case, and in non-deterministic case, the problem is Ackermann complete, so much harder. Yes, so there is a space for improvement, and there is actually still a lot of problems waiting for solving. And we have looked at register automata. So maybe why we have considered language universality problem. There are many problems to consider. Why this problem? So of course it's natural to look at fundamental problems. So maybe the most fundamental would be emptiness problem, but emptiness cannot be easier. So if you take any system, usually you can change it to another system which is deterministic, but emptiness of the original. So the original has empty language if only this deterministic one has empty language. You just change relabel transitions such that every transition has different label, and the new system is non-empty if only the previous the original was non-empty, but it's deterministic. And so we cannot hope for improvement in deterministic or unambiguous case of emptiness, but in the case universality, as we have seen on finite automata, we can hope, and universality is easier in the sense that it can be possibly easier. And as well, like equivalence problem, inclusion problem. Yes, so universality is the easiest of them. So it's natural to look first at the universality problem. But we have also in some cases considered, for example, the inclusion problem. Okay, so what was known before? So first of all, it's known that for non-deterministic register automata, universality is undecidable even for two register automata. So I mean, I denote by this register automata with just 2 registers. Okay, and for register automata with 1 register, it's known to be Ackermann hard, so very hard. Yes, so we can gain a lot, assuming that this is unambiguous, and and this line of work. So even in the case of equivalence, so which is a harder problem than universality, language equivalence here, by equivalence I mean language equivalence. My co-authors, so Antoine Motet and Karin Guas, like 2-3 years ago, they have shown that the problem is decidable for unambiguous register automata, and moreover, a doubly exponential space. And this result was improved. later by Barlow and Clemente to double exponential time. And here is our result. In that case, we have shown exponential space. Actually, independently of us, there is also a better result shown by Bojanci, Klein, and Merman, that the same problem can be done in exponential time and for fixed number of registers in p time, and also the setting is a bit more general. So you can ask, so why am I presenting this work here? So I think that our techniques can be useful also for, so as you will see, these are often quite simple techniques. So maybe these techniques can be used for other systems. Okay. So this is one of our results. So maybe I have to tell you now what are our results. So a following theorem can summarize our results. So first of all, we have shown that inclusion problem for unambiguous register automata is in exponential space. So this is what I have mentioned just a minute ago. Second of all, if you fix number of register to be k, then the same problem is in polynomial space. We were able to generalize our technique also to register automata which take into account order between data values. So in this setting, you should consider rational numbers with order. And then you can transition can be fired, for example, if the input data is bigger from the data value from register 1, but smaller from data value from register 3, let's say. So this is a more general model. And we have shown that the universality problem is in p-space in that case, but actually for one register. And we also have shown something for register automata with guessing. So GRA is register automata with guessing, and GURA is unambiguous register automata with guessing. So we have shown that the problem of language inclusion of language of guessing register automaton in one register guessing unambiguous register automaton is in exponential space. So these are our results. And now I will, essentially speaking, the rest of the talk will be devoted to presenting you the technique on simplified point number 2. Okay, so so about techniques. So this point number 2 was the inclusion problem for unambiguous register automata with k registers. I will present it just for illustration for one register automata and for universality problem. But essentially speaking, if you will see how this works for one register, yeah, like generalization is okay. It's essentially speaking the same techniques, but we need to add something here to think how to generalize it, but the core is the same. You also need to do some Ramsey style techniques in order to generalize from 1 to k. So I will sketch you the proof of this 2' point, and I will compare it to the techniques of my co-authors from 2-3 years ago, and now we have like designed new techniques which are a bit different, and I would like also to stress this comparison. So before, Antoine and Karin have shown exponential space algorithm, roughly speaking, in the following way. So I will call a configuration. So if you start from initial configuration and you read some word W, you can get many locations with many data value. And the whole set of these locations together with data value, I call a configuration. So this is like a set of, of locations plus data values. So if you have some configuration, let's say reachable configuration, in which two data values, let's say 1 and 2, they have the same location. So for example, you both have P1 and P2 in your configuration, Q1 and Q2, and you don't have R1 and don't have R2. Then These 1 and 2 look similar, and they have shown that you can treat them, you can remove one of them, because essentially speaking, they behave the same. So if you have this approach, then you can get exponential bound on the number of data values which occur in your compressed configuration, because if you have n states, you may have 2n subsets of states, and therefore your configuration can be compressed to have at most 2 power n data values, and therefore configuration can be kept in exponential space, and quite easily you can get exponential space algorithm. And our algorithm, which is in p-space, works a bit differently. So we have shown that in universal one register unambiguous automaton, in each reachable configuration, each location has at most 1 datum. So it's impossible that for the same state, you both have q, for let's say state q, you have q and 1 and q and 2. So if we show it, we know that in the size of the configuration is at most size of number of locations. So this is polynomial, and therefore we can quite easily get polynomial space algorithm. Okay, and how this lemma was shown. So now I will show it for you. So let's recall the lemma. So in any universal, we assume that it's universal, one unambiguous register automaton. In each reachable configuration, each location has at most 1 datum. So let's assume towards a contradiction in order to prove it, that in some reachable configuration, some q and 1 and q and 2, q with datum 2 are present. And this reachable configuration is called C. Okay. So, and we aim at contradiction. And we know, so you can assume about your register automaton quite easily, you can show it that every location is useful in some sense. So there is a word accepted from this location, because you can check it, and if it's not useful, you can get rid of that. So we definitely have some words which are accepted from q and 1 and from q and 2. And now the proof will go by case distinctions. We will have 2 cases. First one, so is the following. You know that q and 1 accept some word. Let's assume that it accepts some word such that datum 1 does not occur in this word. And I will present the proof on the example. You will see how it goes on this example. So let's assume that this accepted word is 2343. You can easily generalize it to anything, but I prefer to give a concrete word instead of saying it accepts D1, D2, D3, etc. Yes, so so 1 does not occur in this 2343. So what is maybe unpleasant is that 2 occurs here, and we have also Q2 in the play. But if Q1 accepts 2343, we can change 2 to 5, and Q1 clearly also accepts 5343, because Q1 does not distinguish between 2 and 5. Yes. So, but if Q and 1 accepts this, Q and 2 also accepts this, because 5343 looks the same from the perspective of data value 1 and from the perspective of data value 2. It can be easily formalized and made precise, but I hope you believe me. So then we have 2 runs from the configuration C for this word 5343, and this is a reachable configuration. So actually we have 2 runs, so for some word like the prefix which leads to the configuration C, and then 5343. So this is a contradiction with unambiguity. So this cannot happen. Okay, so let's consider case number 2, that Q1 accepts some word. So what I mean, some word is accepted from Q1, leading from Q1 and finishing in the accepting location. So let's say that this word is 1, 2, 3, 4, 3, 1. So first of all, we would like to get rid of this 2 and be sure that 3 and 4 are also nice. So we can assume that we have some data values, let's say 5, 6, 7, and 8, which are fresh for C. What do I mean by fresh? They don't occur in any location in this configuration C. We can clearly take such data values because there is only finitely many data values in configuration C, yeah, after reading a finite prefix. So if Q and 1 accept this word, it accepts also these words when we change 2 into 5, 3 into 6, and 4 into 7, because from perspective of Q1, 2 and 5 does not differ, and 3 and 6 also do not differ. Okay, so Q and 1 accepts this. So now, before what we have done, we said, okay, this word is also accepted from Q and 2, but here we cannot say it because Q and 2 accepts a similar word, but with 1 changing to 2. Yes, so what to do now? But we can look what if we change this 1 or 2 into another fresh data value, let's say 8. So we have this word 8, and then this 5, 6, 7, 6, and then 8. And it also has to be accepted because our automaton, our register automaton, is universal. It has to be accepted from some. So this is a suffix, so it has to be accepted from some location with some data value in our configuration. Let's say this is P and data value D. This P and D can be equal Q of 1, can be equal Q of 2, can be equal, I don't know, some other location R with data value 2 or R with data value 17, whatever. But we can observe that if data value 1, D, is not equal to 1, then P of D does not distinguish between 1 and 8, because D is not equal to 1. So if it accepted 8, 5, 6, 7, 6, 8, then it accepts also the same word with 8 changed to 1. So then P of D accepts this 1, 5, 6, 7, 6, and 1. And now we have two accepting runs for this word, one from Q of 1 and one from P of D. And this is a contradiction with unambiguity. But what if D is equal to 1? We can show that if D is equal to 1, so in particular it's different than 2, then P of D accepts this other word, 2, 5, 6, 7, 6, and 2, because P of D then does not distinguish between 2 and 5. And we also have a contradiction. So anyway, we have a contradiction with unambiguity. And you can see this kind of place can be generalized, and so this is a contradiction, and this shows that in every reusable configuration, every location can be present with at most one data value. So let's summarize. So let's come back to our results. So these three results were shown by use of this technique, which I have presented to you, a bit generalized, and in the case of 3, you have you have to do more smart tricks in order to show it, and in case of 1 and 2, you have to add some other theory about Ramsey numbers and so on, but it's based on the trick which I have shown you. Here, in the result number 4, we have used techniques which were more closer to the techniques used by Karin and Duan in the previous paper. So we have shown that if we have two locations with the same data values, sorry, if we have the same two data values with the same location, we can kind of compress our configuration, and then size of compressed configuration is at most exponential, and this is how we get exponential space. Okay, so that's all I wanted to say you. Thank you very much.